Welcome to The Explainer. Today, we're going to tackle one of the most powerful and maybe misunderstood numbers in all of science. It's a number that can decide if a new drug gets approved or if a huge discovery makes headlines. We're talking, of course, about statistical significance. So let's just dive right in with a big question. You see the phrase statistically significant everywhere, right? And we're kind of trained to think it just means, yep, this is true. But is it really that simple? Let's dig in and find out. For almost 100 years, this number, 0.05, has been like science's magic number. If a p-value is less than 0.05, it's often treated like the ultimate seal of approval on a research finding. But as you're about to see, the real story behind this number is, well, it's a lot messier. So here's our game plan for this explainer. We'll look at that magic number, 0.05. We'll dive into a tale of two competing theories. Then we'll uncover a missing ingredient called power. From there, we'll see why we need to rethink significance, how power impacts p-values, and finally, what a new rule for research might look like. All right, first up, the magic number, 0.05, the origin of a scientific standard. So where in the world did this 0.05 rule even come from? You might be surprised to learn it wasn't exactly carved in stone. It actually came from this guy, the legendary statistician R.A. Fisher, and he saw it as a pretty simple, practical tool. It was just a way to flag findings that had less than a 1 in 20 chance of being, well, just random luck, or, as he put it, to prevent us being deceived by accidental occurrences. And this part is absolutely crucial. For Fisher, getting a p-value less than 0.05 was not the finish line. It wasn't a yes or no answer. It was more like an index of suspicion. A little flag that said, hey, something interesting might be happening here. We should probably study this more. It was never, ever meant to be this rigid black and white rule. Okay, next section, a tale of two theories, the great statistical debate. Because, Fisher's super flexible approach, it didn't stay unchallenged for long. And this kicked off a huge debate that really shaped how we do science today. So this really lays out the two competing camps. On one side, you've got Fisher, who's basically asking, is this finding unusual? Is it interesting enough to look at again? For him, the p-value is just a piece of evidence. But then you have Jerzy Neyman and Neyman-Pearson on the other side. They wanted a much more rigid system. They said, look, we need clear rules to make a decision between two choices. A null hypothesis, which means there's no effect, and an alternative hypothesis, which means there is an effect. And their biggest contribution, honestly, was this idea that you can be wrong in two totally different ways. You can make what's called a type 1 error. That's a false positive. It's when you claim you found something, but it's not actually there. Or you can make a type 2 error, a false negative. That's when you miss a real effect that was right under your nose. Which brings us to our next section, the missing ingredient, power. Why p-values alone are misleading? Because this is really the heart of the whole problem. If you're only looking at that p-value, you are missing a massive piece of the puzzle, an ingredient called power. So Fisher's world, as you can see here, is pretty straightforward. He starts by assuming there's no effect. That's the null hypothesis. And then he just looks for results that are super rare, the ones that fall way out in those shaded tails of the curve. If something happens less than 5% of the time just by chance, ding, 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 it gets flagged as significant. But Neyman and Pearson's view adds a whole other possibility. They ask, but what if there really is an effect? And that's represented by that second curve you see on the right. All of a sudden, we're dealing with two possible realities, not just one. And that's where those two types of errors can sneak in. Yeah, this visual makes it so much clearer. That tiny black area, called alpha, that's your risk of a false positive, a false alarm. But that bigger, lined area, beta, that's the risk of missing something real. Think of it like a smoke detector with dead batteries. The fire is real, but you just don't detect it. And the ability to avoid that mistake, to avoid the type 2 error, that's what we call the power of a study. It's the probability that if an effect is real, your study is actually sensitive enough to pick it up. You can think of it as the horsepower of your scientific engine. So moving on to rethinking significance and introducing the positive predictive value. Okay, so the p-value helps us avoid false alarms, and power helps us find real discoveries. Using just one without the other is like trying to clap with one hand. So how do we put them together to get a clearer picture of what's really going on? Well, we need to completely reframe the question we're asking. Instead of just asking, hey, is this result a fluke? We should be asking something way more direct, something way more useful. We should be asking, okay, I got a significant p-value. Now, what's the actual probability that my finding is true? And the answer comes from this formula for something called the positive predictive value, or PPV. It's brilliant because it combines the study's power with its p-value. And what it spits out is exactly what we want to know, the real probability that a significant finding is actually true. This is basically our new upgraded definition of significance. And this brings us to the next section, power's impact on p-values. This is the aha moment. Seriously, get ready, because when you see how power completely flips our understanding of the p-value on its head, it's a real game changer. Okay, look at this table. This is what reveals the huge hidden weakness of that old 0.05 rule. If you want to be 95% confident that your finding is the real deal, a p-value of 0.05 is only good enough if your study has a whopping 95% power. Now, watch what happens as the power goes down. The p-value you need to reach that same level of confidence gets way, way smaller. So let's just take a really common example. A lot of studies aim for about 80% power. Well, according to this, for that study, you'd actually need a p-value of 0.042 or less, not 0.05, to be 95% confident. All of a sudden, that magic number doesn't seem so magic after all, does it? Okay, so let's wrap this all up in our last section, a new rule for research, beyond a dichotomous answer. After everything we've been through, what's the big lesson here? How should we really think about the word significant from now on? The biggest takeaway, for sure, is this. Significance isn't some on or off switch. It's a spectrum of confidence. And that confidence, it totally depends on this partnership between the p-value and the study's power. If a study isn't powerful enough to begin with, that old 0.05 standard, well, it just doesn't cut it. And that leaves us with one final thought. The next time you see a headline or you're reading a paper that's bragging about a statistically significant result, you now have the tools to look a little deeper. The first question you should ask yourself shouldn't just be, what's the p-value? It should be, wait a minute, what was the power of the study? Because now you know, that's where the real story of scientific confidence begins.